Welcome back, everybody. So to continue the afternoon and end the afternoon, we have the pleasure to welcome Lajos Diosi, who's a professor at the Wigner Research Center for Physics in Budapest, in Hungary. And Lajos is known for his work on open quantum systems and continuous measurement, and also his discoveries in the domain of foundations, especially on the interfaces between quantum and classical, and quantum and gravity. So Lajos, the floor is yours.
Thank you, Chairman. Above all, I'm grateful to the organizers and to ICTS as well. Since my first visit here, same place, same institute, not exactly the same project, but similar. I grew 8 years older and the plants grew 10 meters higher. So it's amazing. They were just little nothing when this institute was just about being created. Now, the title is not fully covering my topics, but in the first passage, I'm going to answer the question. So that's the first part of my talk. I will consider three families of random trajectories: classical, quantum, and hybrid, which means in my talk, hybrid means classical and quantum. Random trajectory is mathematically a stochastic process. The three different families are classical families, where the value of the trajectory is real coordinate x, t, time dependent. The quantum trajectory is a psi-valued stochastic process, and the hybrid is the combination of the two. I will use the ensemble statistic interpretation, which is common for classical, quantum, and hybrid densities. To visualize it, to visualize this ensemble interpretation, allow me to use this urn or basket model, where the basket is filled with a large number of elements, classical elements, quantum elements, the hybrid elements. In the degenerate case of a pure state, all elements are identical. In the classical case, in the quantum case, as well as in the hybrid case. And of course, if the state is mixed, then the urn contains different elements with frequency according to the distribution, to the density rho. Will be very crucial to consider a basic feature of statistics common for classical, quantum, and hybrid statistics. That's mixing, statistical mixing with some weights in the case of binary mixing, W1, W2. The weights. This is the trivial flowchart. If we mix rho 1 and rho 2, then the resulting density is just the weighted sum of rho 1 and rho 2. And to study the dynamics, again, in all three cases, we study a discretized element of a possible time continuous dynamics. So time continuous dynamics is built up such elementary steps, where M is mathematically a norm and positivity conserving map, and it is not necessarily linear at this stage. So this map is not necessarily linear in rho, but really, could it be nonlinear? All we know the answer, but the simplest proof is not widely known. And the simplest proof is coming from the interchangeability of the operation for which this block stands. So the interchangeability of the operation and mixing. So in the visualized flowchart, this the upper flowchart tells you that the operation, the same operation is applied to both initial states, rho 1 and rho 2, and then comes the mixing, the weighted mixing, and this is the result. On the contrary, when we interchange the order of mixing and operation, the flowchart for it stands here. So first we mix the initial two states. The result, the intermediate result is this. Then we apply the same operation as before to the mixed state, and we got this. Now we got two different mathematical expressions, but be sure that in statistics, the two results must coincide. If you know any reasonable statistical theory where operation and mixing, like here, are not interchangeable, raise your hands. I think that this is a very deep mandatory element, mandatory feature of any reasonable statistical theory, whatever it is, classical, quantum, or hybrid. So if we make these two expressions identical, we get this. What is that equation? What is that identity? It is just the mathematical condition of the linearity of the map M. So it seems to me that this is an elementary proof of the mandatory linearity of classical quantum or hybrid dynamics. And if there is nonlinearity, it invalidates the statistical interpretation. You are in the nowhere. You have no theory. Applying this invalid statistical interpretation is simply illegitimate. But if you still stick to the usual standard statistical interpretation, you apply it, you get very, very strange things. And the most famous anomaly is that you get superluminality. But there are much, much, much more fatal and unacceptable anomalies. We don't know all of them. A few weeks ago, I discovered a new anomaly, which was behind a recent experimental proposal. The failure of a recent experimental proposal, a very recent one. I don't relax the puzzle because I want to write about it when I am back to Budapest. So that was the first part of my talk, the proof, the simplest proof, in my opinion, of mandatory linearity of quantum classical or whatever dynamics. Yeah.
Why it must to commute the two operations?
When I wanted to prove for myself that they must be interchangeable, I use this EARN model step by step. So try to. I'm not able to reconstruct my step-by-step proof using the EARN model, that the mixing and operation are interchangeable, but I propose this to use this EARN model, and maybe after my talk, or maybe tomorrow, I can revive my memory and we can do it. But you can also do it if you use the usual way, the EARN model, that, okay, I pull out a black or white ball from the first basket, from the second, and let it go through the box of map, and I throw it here.
The operation, okay. Can you come back one slide? For example, the operation M can be time evolution.
Yes.
Semi-group evolution. Then, if the evolution depends on the box where you are, it will not come out. Also in classic. If this operation, which is time evolution, if the dynamic of the time evolution depends of the box where you are, of the ball.
No. This is an abstract model.
Yeah, I know.
So there's no time. It's just in model language. It is a quantum channel, say. So apply quantum channel. Of course, in the beginning, you don't know if the quantum channel must be linear, so it is a real quantum channel. Then you prove by these simple arguments that the quantum channel must be linear. So there is no time, in fact. But the time evolution consists of such little boxes, M. And in the next slide, I'm talking about the dynamics, time continuous dynamics, examples of time continuous dynamics. The upper ones are the master equations, which govern the ensemble evolution. The lower ones are, lower equations are for the trajectory. The first example is a trivial one. The master equation is the Liouville equation, and the trajectory, it is just a flow in the canonical, in the phase space. The second equation is for the trajectory, which is running through the phase space, and it is deterministic. It is the special case of a stochastic process. The second example is the Fokker-Planck master equation with friction and diffusion D, which is again linear, and now the classical trajectory is a stochastic process, and here you see the stochastic equations, where WT is the standard Wiener standard white noise, which is the time derivative of the standard Wiener process. And the counterexample is the Boltzmann master kinetic or transport equation, whatever you call it. That's the upper line. This is the same kinetic term as was there in the Fokker-Planck equation, but this term is the so-called collision term, and it is not linear in rho. It is quadratic in rho, as everybody had studied it in any physicist curriculum. So there is no trajectory at all. So this is a famous nonlinear master equation. And we know it is a very nice, useful, effective kinetic equation for the one particle distribution. You can think about a simple example, a simple initial state where this Boltzmann equation would give unacceptable results.
There is a like this, the single particle phase space, rho is the single particle phase space distribution. So the Boltzmann equation is for the single particle phase space, single particle, right?
Single particle,
but
yes.
There is a many body dynamics which gives this, right? I mean,
yes, the many body dynamics looks like this, of course.
But in that sense, there is a trajectory, right? Whose kind of partial.
Yes, it is an effective equation. We thank Boltzmann for it. It is very useful, but it is nonlinear, so it cannot be an exact equation. And I ask you to think about an initial state where Boltzmann equation is giving crazy, unacceptable results. There must be some. Well, now I come to the quantum examples and a counterexample. These are well known for most of the audience, most people in the audience. The first example is the Lindblad master equation, simplest Lindblad master equation. That's the upper line. The second line is the quantum trajectory equation. It is also known for you, and this we will see in below that the quantum trajectory is, of course, not unique. And there are infinite many unravelings for any non-trivial Lindblad equations. And in this case, I chose the so-called quantum state diffusion process, where this random noise is not the white noise, not the real white noise, it is the so-called Hermitian standard white noise. So it is a complex white noise with a specific feature that the expectation, that the correlation of psi with itself is always zero. And the correlation of psi with the psi star is the delta function. So that's the mathematics of the so-called quantum state diffusion unraveling. The second example is the positional decoherence. This is probably the simplest Lindblad-Master equation, which describes the decoherence in position. Now, as we all know, the unraveling, I mean the statistics of quantum trajectory is non-unique. We have infinite many families of quantum trajectories that yield the same master equation on average. Here I chose two of them. The first one is the Brownian motion, where the randomness comes again from the standard white noise. And of course, yes, I simplified my equations not using the Ito formalism, and I forgot to insert here the Ito correction. So there is a nonlinear term similar to this in here. But this is the naive form of the unitary unraveling belonging to a positional decoherence. And the second one will reappear in the forthcoming parts of my talk. The second one corresponds to the wave function localization. And sorry, this must be the real WT. I made a mistake. So this term is responsible for the localization of the wave function, and this term restores the linearity. This term is responsible to restoring the linearity of the master equation, which is the evolution equation of psi average. And the counterexample, which I only mention here, is the Schrödinger-Newton equation, which is the Newtonian non-relativistic limit of the standard general relativistic semi-classical gravity. Here we don't have the master equation. We only have the nonlinear Schrödinger equation. It is nonlinear because V of psi is the mean field generated, mean field gravity, mean field Newtonian potential generated by the density represented by psi dagger. Okay, in some special cases we have the master equation, but for generic mixed states it doesn't exist. Now, hybrid trajectories and the prototype of them. Here you are. This is the stochastic master equation of position monitoring, where the outcome signal is x of t. It is the measured value of operator x. And we introduce a new variable instead of x of t, which is uppercase x of t. And you will see the reason of this replacement of this standard signal by this integrated signal, uppercase x, because then both equations of position monitoring contains the time derivative. One is the time derivative of the quantum trajectory, and the other one is the time derivative of the signal. This is already our prototype hybrid trajectory. Now we want to develop the theory for the master equation. Therefore, we introduce the hybrid density. This is the definition of the hybrid density. Mean means stochastic mean. So we have to average over xt and pt according to these two trajectory equations. And of course, the reduced density, the classical reduced density is the trace of the hybrid density. The reduced quantum density operator is the integral of the hybrid density over the classical variables. And this guy is the conditional quantum state. And if you invest some minutes, maybe some hours, to derive the master equation of the hybrid density, starting from the stochastic equations here, then you get this result. And as you see, it is of course a linear master equation. It is equivalent with the stochastic trajectory formalism of the hybrid system. And if you look at it, you might cancel the decoherence term and the diffusion term. And you might think that this little simple deterministic coupling, I mean, in the sense of the master equation, this simple flow would be enough to get the footprints of the position on the classical variables, on the distribution of classical variables. Now, the case is not so easy. Without this decoherence and diffusion terms, this evolution rule wouldn't preserve the positivity of the hybrid density. So the rule is that whenever you couple something which is classical, whatever it is, it might be a canonical system, another classical canonical system. In our prototype example, it is not just accidental. This prototype is very important. So in our prototype example, the classical variable is not a canonical variable of another classical dynamical system. It is just the measured signal, the measured integrated signal of quantum position monitoring. So we these two terms are able to guarantee the positivity of rho as it is evolving according to this master equation. And you may say that there's the gamma is here up and the gamma here is down. So the consistency, the positive preserving feature of the equation is guaranteed if it might be guaranteed if you higher the rate of decurrence and lower the diffusion, or the other way around. But this is the so-called minimum noise master equation. Given this coupling, these two terms represent the minimum noise if one is proportional to gamma and the other one is proportional to 1 over gamma. And in this case, this equation is purity preserving. If initially the quantum state is pure, then it remains pure forever. Now the general hybrid dynamics. I'm using the lessons of the previous, from the previous slide. General hybrid dynamics means coupled dynamics of a classical, not necessarily dynamical, as I noticed, a subsystem on the one hand, and a quantum subsystem on the other hand. The verdict, the lesson is the following. About an individual quantum system, the random measurement outcomes are the only true, some years ago I used tangible, the adjective tangible, classical variables that are legitimate to be coupled to any other classical variables. The famous counterexample, which is illegitimate when you want to couple it to classical variables, the paradigmatic not true classical variable is the mean value. The mean value. We have billions of very useful, effective mean value equations in from the laser physics to cosmology, the semi-classical, the famous, very, very useful theory of combining gravity and quantum mechanics is the semi-classical, that is mean field gravity, which cannot be a fundamental consistent equation. So that's the main message of the second part of my talk. And accordingly, the dynamical action of the quantized subsystem on the classical subsystem is only possible via the stochastic classical signal of quantum monitoring of some quantum observables of the quantum subsystem.
Yeah. Lajos, did you turn off your mic, maybe? Did you turn off the mic in your pocket? Because your mic is not on anymore. No, I'm saying your mic is off.
Sorry.
Thank
So
you.
before I come to my last slide, yes, the painful lesson that if you want to couple your qubit or any two-level system to a classical oscillator, mathematically and fundamentally consistent dynamics will become irreversible, because you must have a recurrence term and you must have diffusion in the oscillator, in the classical oscillator. And here you see the hybrid dynamics flow charts. The upper example is the simplest one, where the classical subsystem is not a dynamical subsystem, it's just the signal, which is measured, and that's the simplest hybrid dynamics. Now, you can use feedback from the behalf of the classical system toward or on the quantum system. And if you, typically, if you want to couple, say, a canonical, okay, let me put it simpler. If you may have further classical subsystem or subsystems. Here for them, Y will stand. Then this is a flow chart of a possible more complex dynamics, but observe that there always must be a substructure of monitoring. So the structure is such, in this case, it is not the most complex block, that as before, X is the monitor signal, Y is waiting for taking part in the dynamics, and then this is a linear map which represents the interaction between the subsystem X, which is the monitor signal, and the subsystem Y, which can be whatever other classical subsystem. And then you may have feedback from these classical parts or from the others. And of course, I forgot to draw a block of M, completely positive operation on here and there. So that's a typical complex structure, and the part which is always there is this. So that's the summary. You may already forgot the first part of my talk, that the linearity of classical quantum and hybrid dynamics follows from the basis of statistics. Second, the stochastic master equation formalism, trajectory formalism, and the hybrid master equation formalism of quantum monitoring are totally equivalent. The next lesson, hybrid dynamics contains quantum monitoring. It may contain self-dynamics of the signals coupling to further classical subsystems, and feedback controlled by the classical variables. And there are dozens of colleagues who contributed to our current knowledge about hybrid systems, especially. Let me enhance the role of Anton Tilloy and Janet Oppenheim's group. And it's time to stop, and thank you for attention.
Thank you, Lajos, for your talk. Does the audience have any question? Yes, Tristan.
And without revealing your new idea, do you have any other examples of the consequence of nonlinearity on like weird consequence that we accept of like on top of superliminic communication? What are other weird consequences of nonlinearity?
Yeah, those ones which I am ready to disclose are so the context of superluminality is fake action at a distance. So even if you forgot about Albert Einstein, forgot about relativistic causality, you observe that non-linearity of the Schrödinger equation will give you fake actions at a distance, which are non-physical. And the other one is technical. It's that nonlinear Schrödinger equations, in the general case, are not applicable to mixed states. In some situations they are, but generally, if you are just presented by a mixed state here in your lab, and somebody asks you, please calculate the fate, the future of this mixed state using a nonlinear Schrödinger equation, you are in trouble. You don't have answer.
I have a question. Can you go back 2 slides before? So my question is, you're saying the only way to couple a quantum system with a classical system is through these measurement outcomes. Is this a mathematical argument or a physical argument?
Yeah, whenever I claimed anything that it must be so and not the other way, I simply I economized with my time to talk. Otherwise, I would have admit that there might always be some hidden assumptions which I don't even know, which I don't mention, and so I think it's more than the opinion of a physicist. It is much more than that. So actually, I don't know how to prove this statement. So but I stick to it strongly.
Any other question? Otherwise, I have another question. So you say that because of the way we build our probabilistic theories, our statistics, this enforces linearity of the evolution. Yeah. Do you see any ways around this? Is there anything we can change to have nonlinear equations that make sense statistically, or do you think this is like, if you want to no-go, like that it has to be linear or whatever the cost?
I don't precisely understand your in what you are interested.
I'm thinking, imagine, for example, some dynamics which would be nonlinear.
Yes, some what?
Some dynamics.
Some dynamics which is nonlinear.
Which is nonlinear, but maybe doesn't allow you to use supraluminal communication because it's in such remote circumstances, such remote parameter regimes that you actually physically cannot use it. Should we allow this kind of dynamics? Should we bypass a little bit to only...
in fact, there are arguments that if you want to... the Grossart group in Germany studied the anomalies of the Schrödinger-Newton equation. I mentioned it to you. And to observe the superluminality, you must be very fast. And it might be that technically you can never be that fast enough to observe the superluminality caused by this gravitational nonlinearity, which is there in the Newton-Schrödinger equation. And also there are speculations that if we add some spontaneous collapse mechanism, which are formulated by independent theories, independent of nonlinear Schrödinger equations. So if we add some irreversibility, some loss of information and coherence from the beginning, then we can mitigate again superluminality. And the best way to eliminate superluminality, if we find some alternative stochastic interpretation for the wave function, we might retain the standard stochastic interpretation in classical statistics, but we might invent some modified statistic interpretation for the wave function, so in the quantum world.
Thank you. We have another question.
It works? Great. Thanks for the talk. I loved the Boltzmann equation example. It makes a lot of sense to me because basically what you're saying, imagine I have a gas at some temperature, I have the Boltzmann function. Now I say, I don't know, maybe gas is at temperature 1, maybe it's at temperature 2. The Boltzmann equation would predict it to thermalize in the middle, whereas in reality it's either there or here. Nevertheless, Boltzmann equation is very useful. Yeah. So this means that if I want to have a quantity which I can combine with probabilities, which I can interpret statistically, it must be linear. But just as Boltzmann equation shows, just as other examples you said show, also other examples exist. Even the simplest, I have a particle, its coordinate, evidently, if I say maybe particle is here, maybe particle is there, its trajectory will not be the same as trajectory of the middle point. Nevertheless, the coordinate of a particle is a useful quantity. So what I wanted to ask, is there any general argument when I should use statistically interpretable quantities, and therefore this would force me to be linear, and when I can afford to use quantities which do not have statistical interpretation? Is there some sort of general consideration for that?
It is already the project of a new statistical interpretation, because I think that any physical quantity has its statistical interpretation. It is a deterministic quantity, then it is the degenerate case of statistics. If it is random stuff,
well, nevertheless, the Boltzmann equation is kind of in the middle. It describes me the probability to find a particle, but the particle in a gas under very specific conditions. I do not allow to combine probabilistically two gases at the level of single particle distributions.
I admit that I have been thinking about a sharp proof why Boltzmann nonlinear kinetic equation would create craziness.
Mm-hmm. Okay. Anyway, thank you. Thank you. It was interesting.
I called you to compete for best, craziest, simplest anomaly of the Boltzmann dynamics.
Okay. Thanks.
All right. Thank you again, Lajos, for your talk.